the zeros in because nothing is there. And I know I have some auditors in here that I'm not always going to see something posted, and that's okay. But there has been one instance where someone was positive they submitted it, and I said, really? So, yes. And that something happened. And so when you submit, make sure that you go back and look at it. And I make the assumption you can go back and look at what you submitted. Can you?
Yeah.
Yes. Please go back and look to make sure it's actually there before you just assume that you hit the right button and that you didn't do something else like close it out and not save it or whatever happens. Because I've seen lots of blank ones, and on one occasion I saw one where it was just a fragment of a sentence, and it was very obviously something happened, but it wasn't cut and pasted right, it wasn't all there. So please double check. Okay, we're going to do chapter 21, and we're going to go until I fall over.
Oh, good.
Or my voice gives up, or whatever happens. Okay, so chapter 21 is amino acid metabolism. And this is something that's constantly going on inside the cell. So proteins are constantly being synthesized. And degraded inside the cell. Okay, so they get recycled. And so what we're going to talk about first is not really using amino acids as a fuel, but just what happens in general to any proteins that you happen to make. So we're looking at protein degradation. This can happen in a couple of ways. So this can occur in lysosomes. And this is a process that happens both in prokaryotes. And eukaryotes. And lysosomes have lots of hydrolytic enzymes. And so if we're breaking down proteins, those are going to be proteases. Lysosomes are also acidic. And it includes breakdown of nutrients that have been brought in by endocytosis. But these compartments are also used to degrade regular cellular components. So that's one way you might see proteins get degraded in the cell. But there's another process, and that's the ubiquitin pathway. So the gradient is called proteasome. This is something you're going to see in eukaryotes. 26 amino acid protein. And it gets its name because they found it everywhere. So it's ubiquitous. They found it everywhere before they knew it did. If you are a protein that has been targeted for degradation, then it gets covalently linked to ubiquitin. So the ubiquitin protein itself is kind of a signal to say that this protein I'm getting attached to needs to be degraded. And your attachment occurs in 3 steps. Uses a ubiquitin activating enzyme. So ubiquitin, we're going to call it UBI. And it's got a C terminus somewhere. But somewhere there's a C terminus. And then my ubiquitin activating enzyme has a cysteine side chain on it somewhere. Form a bioester between them. There's my ubiquitin. Here's a C terminus, and now I have a bioester with it to B1. Okay, this requires ATP. And it gets hydrolyzed to AMP plus PPI. And this process can be pulled forward. By hydrolysis of the PPI, which is also energy releasing. So, ubiquitin activating enzyme, what class of enzyme is this? Ligase goes up. That's usually the thing. Why is a ligase? Used ATP and it did what?
Made a bond. Made a bond.
Made a bond between 2 things. They joined them together. That's what I was just thinking. Alright. So if we're eventually going to stick ubiquitin to our target protein, but we started off by connecting it to this other enzyme instead through a bioester, which is going to be for this kind of high energy linkages. So this is now activated, and we're going to end up putting it onto our protein, but it still takes 2 more steps. So the next one is ubiquitin conjugating enzyme. Which is the second one we need. So here's my ubiquitin with its bioester linkage to first enzyme. And my E2 also has a cysteine side chain on it. And basically we're just going to swap them. So E2 comes in and E1 leaves. And so now ubiquitin has a bioester to E2. And then the last one is ubiquitin protein ligase. So the ubiquitin with the bioester E2. This will be 3. Okay, and then I have I was going to say this is my protein targeted for degradation. And so it's going to come in, E2 is going to leave, and now my ubiquitin is attached. Now through an amide, to the protein. And this is a lysine side chain. What kind of protein doesn't have a lysine? Yeah. Yeah. There's an interesting question. Are there proteins out there that don't contain lysine? And my guess would be no.
Should we make one now?
If you wanted to.
Yeah.
But I mean, ubiquitin pathway is not the only pathway for protein degradation. Ubiquitination is repeated, and you can form polyubiquitins. Where you have your protein that is attached to a ubiquitin that has some C terminus somewhere that is attached to another ubiquitin, and you can keep going. So ubiquitin gets ubiquitinated too. And it takes a minimum of 4 tandem ubiquitins. Because sometimes your proteins do death. Death by proteasome.
If you go up just a little bit, is the, next to the, ubiquitin, it's the carboxyl group, not the methyl group, like it's shown, not methyl, the nitrogen group like it's shown below, or?
Oh, whoops, sorry.
Okay.
Let me draw that.
Oh.
Sorry, it's through the lysine, you're right. So it's the NH this way to the carboxy.
We can't see.
Oh, no. Very good. Sorry. Protein through the lysine to the ubiquitin, but then the ubiquitin has a lysine on it somewhere.
Okay.
There we go. That goes to the C-terminus of another ubiquitin. Yeah, I drew it backwards. And then that continues.
Does that mean there's like polyubiquitinated, just ubiquitins floating around? Like those aren't attached to a protein? And then if you activate one that is attached to another ubiquitin?
That's a good question. I don't know if you ever. So when the ubiquitin gets recycled, but I don't know if it gets recycled only as monomers or whether it gets recycled as polyubiquitinated species. When you isolate the proteins that are ubiquitinated, they have multiple ubiquitins attached. So I don't know if you could attach a polymer eventually or not.
Sentence protein to death. By proteasome.
Why is this being painted?
The link though has a meaning. And that is related to the lifetime of the protein. So if you go into the cell and you look at how long or how quickly proteins get recycled, it varies depending on the protein. So there's a table from your book where it's half-life in hours before it gets degraded and recycled. So you got some things that are pretty short, they're only around for a few hours, and then you've got other things that are around for a long, long time. But everything gets recycled on this kind of continual basis. So then there's the question about how does ubiquitin depletion enzymes, how do they know which ones need to stay around and which ones don't? And that is due to the end-end rule. So your degree of ubiquitination is dependent on the end-end rule.
That's not confusing.
And so if you are D, R, L, K, or F at the N-terminus, the protein will be rapidly ubiquitinated acid, arginine, leucine, lysine, or phenylalanine. If your N-terminus ends with an A, G, M, S, T, or B, have the N-terminus. The protein is slowly ubiquinated.
Why,
I'm waiting for this question. Yeah.
why is that?
Oh, why is that? That wasn't the question. Why is that? That's how the cell knows which proteins need to be turned over rapidly and which ones don't.
What's the question you're waiting for?
What if you're not one of those?
Well, if you're not one of those, they're probably somewhere in between.
Oh.
Maybe not. Sorry, let's go.
Now the question I'm waiting for is, how can the N-terminus start with anything but an M?
Isn't that the mechanism?
So, whenever you have a messenger RNA that codes for a protein, the first codon is always a methionine. There's always a start methionine. And so then that makes you think, well, then every protein should start with a methionine. But they do, they get degraded. Or post-translationally modified so that it's a different N-terminus. That was the question. Okay, there's other ways to determine what ought to be degraded fast. There are proteins called S proteins. They're also rapidly degraded. And these contain regions rich in chromium, glutamic acid, serine, and threonine. These regions get phosphorylated. As a signal to be ubiquitinated. Okay, so we have serine, threonine, side chains, and we get phosphorylated. Okay, so if I'm a protein and I have at least 4 ubiquitins attached to me in a row, and then I'm going to get targeted to the proteasome. So ubiquitinated. Are degraded. Proteasome. This is a multi-protein complex. It is a 26S particle that is composed of 2 times 19S caps plus 1 20S cylinder. Now for the next question.
Where does 26 come from?
Yeah, that's a good question. Maybe even before that, what's an S? S is a what? leave your centrifugation stuff for lab, those are real bad. Did we talk about S's at all? Trinity didn't. I have to go back and look. S stands for Spedberg. Of course it does, yes. But that, remembering the name of the guy who came up with this, that's not always so easy. You can think of S as for sedimentation. And it is, this S term is a sedimentation constant. So it's basically looking at a sedimentation rate if you spin a solution containing this protein in a centrifuge. And so that's related to size, because the bigger it is, the easier it is to pellet it when you centrifuge it. The smaller it is, the harder it is to pellet it. It's not going to sediment out very quickly, it's tiny. And so it's related to a mass, but notice it's not additive. Yeah, so two 19s, 19 plus 19 plus 20 does not add up to 26. And so that's sometimes disturbing. So it is related to how big the particle is in the mass, but it's not additive. And part of that is because your sedimentation rates are dependent on not only on the mass of the particle, but also the shape. So it's just kind of a measurement of, so I'll say it's related to size and shape of the molecule. So the cylinder, this has 28 subunits. And these are alpha and beta subunits. And the betas have this catalytic activity that we hear about. So beta 1 hydrolyzes peptide bonds at acidic amino acids. Beta 2s hydrolyze basic amino acids, and beta 5 hydrolyzes hydrophobic. It's big. Anything that they're measuring in Spedberg units is big. And it's big enough that you can see it with electron microscopy. The middle, here's the cylinder. The 20 cylinder, there's a 1 nitrous cap, and there's another 1 plus cap. And then the cylinder has all these subunits, these alpha and beta subunits, some of which have this protease activity, where they'll break up proteins. So your cylinder is going to degrade your UV proteins down to approximately 8 residue fragments. Yeah, that's going to vary. And then other cytosolic peptidases finish the degradation. Down to single amino acids. recycled intact. And again, I'm sorry, I don't know whether that is in monomer form or polymer. The caps, that isn't quite as clear, but these seem to help target the UV proteins to this element. And last thing to note is that everything we just talked about is just eukaryotes. Prokaryotes also use self-compartmentalized.
Can you shift it up?
Yeah. Proteases, so they resemble the proteasome in function, but they look different. And for the sake of time, we're not going to cover those in detail.
But prokaryotes don't have ubiquitin.
No, so this is not a ubiquitin pathway. So that's looking at the breakdown of proteins inside the cell, which is different from dietary proteins. So if we look at dietary protein degradation, this is broken in the digestive tract. So it's going to be broken down in the stomach, mostly by pepsin. Which is a gastric protease. And then it's further broken down by pancreatic proteases in the small intestine. And so that includes your trypsin and chymotrypsin. Small peptides and amino acids can be absorbed across the intestinal lining. And can enter the bloodstream. Pretty much as it is. Further degradation then is going to happen at the cellular level, like we just talked about. But at that point, we're already down to small peptides.
Yeah, go first.
Okay, so proteins inside the cell, we chop it up into single amino acids. Dietary proteins, in the end, they eventually get chopped up into single amino acids. Amino acids can be used for fuel. That's not your first choice. Your first choice is always glucose. But under starvation conditions where you don't have any glucose, you don't have any glycogen stores, you can break down proteins for fuel to be oxidized. And so that's what we're going to spend most of the time is looking at that. So this is metabolism of amino acids. And this begins with deamination. Amino acids don't look so different from carbohydrates if we can get rid of the amino group. And so that's the first step, is to get rid of that amino group. So this removes the amino group, initially as ammonia, and then it'll get converted to urea, and then you can excrete it. Deamination forms what's called an alpha keto acid. And this happens in how many steps? How many steps do you want?
3.
Two's a good number.
0 steps. It just happens.
Okay, first step is actually transamination. The alpha keto glutarate to make glutamate and an alpha keto acid. So we have 20 different amino acids, and with the exception of lysine, which doesn't work this way because lysine's got more than one primary amine on it, they all are going to go through this transamination before the deamination part of it. And part of that is just how many enzymes do you need. So you can think of this as kind of conserving resources, because you might have lots of different aminase enzymes that recognize different amino acids, but then if you move the amino group to one amino acid, in which case glutamate is the one amino acid we're moving it to, then you only need one deamination enzyme. Okay, so rather than having 20 sets and then another 20 sets, we have 20, or they recognize more than one, but we have a certain subset, and then we have just one at the final deamination step. Okay, so we're going to draw these out. Generic amino acid. We got a C terminus, or carboxyl group, amino group. Some R group. That's not lysine. And hydrogen. So that is my amino acid, whatever it is. And then we're going to add this alpha ketoglutarate. Okay. That is basically just a glutamic acid using its amino group. And it's an alpha keto because the keto carbonyl here is one carbon away from the carboxyl group. And then we have our or amino transferase. And we're going to swap some functional groups. And I'm basically going to swap my amino functional group for my keto functional group. So now I have my new alpha keto acid. which alpha keto acid depends on what amino acid came in. And I have glutamine. The mechanism is actually pretty complicated. It requires a PLP coenzyme, and that's a vitamin B6 derivative. And it's going to use covalent catalysis. It's also going to use some acid-base catalysis. And in the covalent catalysis, this is an example of a shift base formation that we're going to do. And again, these are all amino acids are deaminated this way, except for lysine.
So what happens to the glutamic acid in the body if we're trying to break
Well,
down?
it's going to get acted upon right away. This is just step one of our two-step process to deaminate an amino acid.
Okay.
So your glutamic acid gets converted right back to alpha ketoglutarate at the second step.
Oh, okay.
Okay, so here's my PLP, was a derivative of vitamin B6. And then this is the PLP. We've seen this a few times before, where it can form a shift base to something. It could be to substrate, it could be to your enzyme. And we're actually going to form a shift base to both in the mechanism. So your PLP starts as an enzyme, coenzyme, covalent complex. So it's actually linked to the enzyme, and it's linked through that shift base formation. So that's at the end of the lysine side chain, somewhere in the enzyme. And then you have your alpha amino acid, amino acid coming in, and basically we're just going to swap the nitrogens in the shift base. So it's not really a hydrolysis of the shift base. It's although I suppose you're hydrolyzing with another amino acid. So this nitrogen comes in and attacks, and then you get this diamine intermediate, but then the enzyme leaves, so here's the enzyme hanging out, and now I have a substrate coenzyme covalent complex. And again, it's just a shift base formation. This thing, we can pull a proton off, and so here's your acid base, if your base catalysis, there's an acid base, so we make the proton off. And normally you can't make protons off of carbons, except that the shift base complex, in addition with the ring that we have down here, gives you a nicely resonance stabilized carbanion. So it's okay. That hydrogen is actually somewhat acidic. You can pull it away. And so then you have your hydrolysis part of it. So when the hydroxide comes in, and we're going to hydrolyze that shift base. And basically remove the amine. So we're going to leave the amine with the PLP. That's on the next one. There we go. Okay, so we have our hydroxide coming in to hydrolyze it, the touch neutral intermediate. But then the amino acid leaves, but it's left behind its amino group that was there initially. So now I have my alpha keto acid, and I've got the amino group that came from it stuck to that PLP enzyme. Okay, so that's just the first half though. That is the half that gets the amino group off of my amino acid. The second half has to put that amino group onto the alpha-ketoglutarate to make glutamic acid, and it is the exact reverse of that mechanism. So it just goes exactly backwards. So it's just a series of shift base interconversions, basically, and then hydrolysis of it. Okay, so that gets our amino group off of the amino acid that we want to degrade. And then the second step is to get it off of the alpha-ketoglutarate, because we don't want glutamic acid. And so step 2 is an oxidative deamination of glutamic acid to make ammonia, and it actually will leave as an ammonium, because ammonia is not very soluble, but ammonium is very soluble. To reform alpha-ketoglutarate. Okay, so here's my glutamic acid. And this requires, it's an oxidative deamination, so you're going to have some redox happening here. And this is actually an NAD, and it depends on organism source what you're looking at. Sometimes it's an NADP. But it requires one of our electron carrier cofactors. And it's going to get reduced. And the enzyme is a glutamate dehydrogenase. And I'm losing some electrons and some hydrogen, and actually what you form is this amine intermediate. So we're going to pull away the hydrogen from the alpha carbon and make an imine. So this is kind of a transient species. This is an alpha amino glutarate. And then water is going to come in and hydrolyze the imine. Again, this is just like hydrolysis of the shift base. And the ammonia leaves as a water-soluble ammonium ion. And now I have my alpha-ketoglutarate back. We don't excrete ammonia, we excrete urea. And so we have to have a mechanism to get rid of the ammonia. Otherwise, it would build up to toxic levels in our blood and we'd all die. Yeah. So, and once again, it's going to be our liver, and of course the rest of you to do this for us.